The leap from traditional calculators to the power of computer programming really begins when we turn to variables, operations with variables, and input-output commands. Let's start with variables. Now, even though the word variable is used in math, don't think that this will be like high school algebra. Instead, when you hear the word variable in computer science, think of a box. In fact, you can think of computer programming as based fundamentally on boxes, setting up boxes, assigning things into boxes, and doing things inside and among boxes. The manipulation of variables in working memory is what allows computers to become the flexible, powerful, general-purpose machines that we all depend on. Now, this might seem surprising, since the aspect of a computer that people usually think of first is the processor. Like this one. This is a central processing unit, or CPU. That's where all of the operations that our computer has come to be processed. But by itself, the processor is just a very fast but very dumb calculator. Take a look. The processor is located on a board, the motherboard, where you've got a whole bunch of stuff all connected together. Now, this is where memory comes in. Memory is where the variables in a program live. Without memory, a computer can still process operations at a very basic level, just doing some very basic arithmetic. But for the computer to operate at a higher, more complex level, really to do anything beyond the absolutely most basic operations, it needs memory. Computer memory is actually composed of several layers, categorized by how close they are to the processor. The closer to the CPU, the easier and faster it'll be for the CPU to access that memory. As you get farther away from the CPU, it takes longer to access the memory, but you get more of it, and it generally becomes longer lasting. Critical data may be moved from one layer to another as needed. Now, there's some memory called the registers built right into the CPU, and some other memory, the cache, that's in the same integrated circuit as the CPU. This is all really short-term memory, and most programmers don't really need to worry about it. The next level of memory is the main one programmers care about, and it's actually called main memory, or sometimes primary memory. This is the main short-term memory of the computer. It's the working memory where we keep all of the things that are running, from the operating system that we're working inside of to the programs that we're currently executing. In our demo computer, the main short-term memory is connected to the motherboard, over here. The memory is still close to the CPU. It's directly connected on the motherboard with a really fast connection between these two. This memory is the RAM, the random access memory, that we see referred to in a computer's specs. It's called random access because every physical location is accessible with equal speed. However, the way existing technology works, if we lose power to the computer, the data that's in this memory is lost, which is why it's also referred to as volatile or temporary memory. When we talk about variables in memory, we're talking about variables held in temporary memory. When we run a program, part of this temporary working memory is set aside for use by variables in the program. Now, if you look farther away from the CPU, over here, you get to memory that's in so-called permanent storage, what's also called secondary memory, or just plain storage. And whether it's a hard drive like this, or a solid-state drive using flash memory, this is where we store longer-term information, like files. As programmers, we deal with storage by deciding what data we want to read in for attention in temporary working memory, or write out to files back in storage. Now, beyond secondary memory that's on board the computer, there's also what's called tertiary memory, or remote storage. This is data that's stored more remotely, possibly offline or over a network. Remote storage can store massive amounts of data, far more than you could have on your own little computer. The idea of cloud storage is that the computer gets to treat this tertiary memory more like secondary memory. As time goes on, there will probably be less and less distinction between local and remote storage. Okay, let's talk about how all of this relates to the way we write code, starting with main memory. Again, a good way of thinking about this temporary working memory is as a set of boxes. It might even help to think of an actual physical box. Now, each box can contain some piece of information. If we want to use these boxes, we need to be able to refer to them, so every box is going to have a name. It's these boxes, these regions of memory that have a name and can hold a piece of information that we refer to as variables. Variables in programming are similar to the variables like x and y that you've used in algebra in that they can take on different values. But in programming, variables are much more flexible. Each of these variables, the boxes with a unique name, can be used to store information. And to do this, we'll have to do a variable assignment. Now, what if we want to have a variable x, and we want that variable to hold the number 3? Well, we can write this with a line of code, x equals 3. The left-hand side of an assignment is always going to be the name of a variable. It's the name of the box that we're assigning into. In this case, the box is named x. Now, the next character is an equal sign. But it's important to realize that this equal sign does not really mean equals, at least in the way you're used to thinking of it. It's actually what we call an assignment operator. That is, it's indicating that we're assigning a value to a variable. The assignment operator always takes the thing on the right-hand side and assigns it to the box on the left-hand side. In this case, the thing that's on the right-hand side is a number, the value 3. So, the overall result of this line of code is that we take a box of memory with the name x, and we put the value 3 into that box. Now, to be clear, this does not mean that x is now and forevermore equal to that thing on the right-hand side, the 3. This convention of using the equal sign to mean assignment is pretty widespread across computer languages, going all the way back to Fortran. All this means is that the variable x has been assigned the value 3. If it helps, you can use the words is assigned when you see this equal sign. Now, the right-hand side can actually be something more complicated. It could be numbers with a decimal point, which are called floating point numbers, or floats for short. Or we could assign words. For example, x is assigned the value make pizza. Expressions in quotation marks are called strings, since they're formed by characters strung together. The string can be enclosed within either single or double quotation marks. Both work the same way. Remember, though, that you need to have quotes to have a string. Pizza in quotes is a string, but pizza without quotes could be a variable name. If you're trying to refer to the actual letters of the text, you have to enclose the text in quotes. Let's look at variables in a just slightly more complex example. Let's say we follow the previous assignment with a new assignment. Y gets assigned x. Now, we have another variable named y, and we're assigning a value to it. The value to assign to y is the thing on the right-hand side. In this case, that's the variable x. So, when this code executes, we first execute the first line. X is assigned 3. And we create a box, a memory location labeled x, that contains the value 3. When we execute the next line, we'll take whatever is stored in the box named x and put that value into the box named y. So in this case, both x and y end up with the value 3 inside. Now, let's say that we have a third line of code, where we assign a value 5 to x. Notice that the value of y is unchanged. It doesn't matter how y was originally defined. All we care about is the current line of code and what it changes. So, assigning 5 to the x variable has no effect on y. Remember, the equal sign is an assignment operator, and it just tells us to take that thing that's on the right-hand side and assign it to the one on the left. it does not mean that these two things are forever equal to each other. So, when we have an example like you see here, it's critical to understand that changing the assignment to x does not make any change at all to y, and vice versa. As we write programs, we're using variables to keep track of information, and this means that we'll need names for each of our variables. In Python, you can name variables anything you like, subject to a few rules. 1. Use only letters, numbers, and underscore. And 2. Don't use a number at the beginning. So let's check. Are all of the following valid variable names? Test program, game1, castle underscore anthrax, question 3 underscore a? Yep, all of these are perfectly acceptable variable names. We don't have to follow English spelling rules. Okay, what about these? New underscore years underscore day, first dash name, one game, cheese shop? Nope, all of those are invalid. They contain characters like apostrophe, hyphen, a beginning number, and a space. If we use any of those, we'll get what's called a syntax error. Oh, one other rule. A few of Python's built-in commands, such as print, are known as keywords and should not be used as the name of a variable. Now, as long as we follow these rules, the computer doesn't care what we name variables. We just need to be consistent. However, code is written for people as much as for the computer, and so it's important to pick good names. If you're familiar with the story of Adam in Genesis, you might remember that just about the first thing we read of him doing is giving names to animals. Names are critical because we use them to help us understand and clearly refer to the world around us. Similarly, names are important in programming because they help us understand and clearly refer to the variables that we're dealing with. It helps set up the framework and the mindset that we'll use when we're approaching the problem. If I see a variable named x, that doesn't really tell me much. But if I see one named interest rate, I have a pretty good idea that that variable is giving me an interest rate. So, as we write code, we'll try to use good names whenever possible. Of course, if we're doing math, or we're illustrating a similarly general point, we can use generic names like a, b, x, y, and so on, just like we would in math. Now, all of this brings up the notion of variable types. Every variable has a type, which is the way that the piece of information inside that box should be understood. In this example, a is an integer, -5, b is a floating point number, 3.14, or just a float, and c and d are both strings. In some languages, you need to be very particular about specifying the type of a variable. In Python, it'll figure out what the right type is based on what's assigned. But you do have to be careful that you understand the type, so that you don't make a silly mistake. You don't want to perform division on a string. Now let's turn to operations on variables, which brings in the processor. One of the most basic operations that computers can do is simple arithmetic. Your standard operations like addition, subtraction, multiplication, and division, those are all built right into the CPU itself. Variables in our program can use these operations to compute new values, just like a calculator would. Take a look at this sequence of code. A, B, and C are variables. And notice how A is used to define B, and then B is used to define C. So, we can assign the variable A the value 2 plus 5, which the processor evaluates, adding 2 and 5 together to get 7. So, when we assign a value to variable B, we can use the value that's in A. So, if we assign A minus 4 to B, then since A has the value of 7, A minus 4 is just 3, and this is the value that gets stored in B. Then, when variable C gets assigned the product of A and B, the values sitting in boxes A and B are 7 and 3. So their multiplication evaluates to 21, and that's what gets stored in C. To see how one variable can be used by another, Imagine a case where you want to calculate the value of an investment after earning interest. Let's say that we've got 4 different variables. Interest rate, defined here as 3%, principal of 1,000, interest earned, given by the formula interest rate times principal, and total amount, which is principal plus interest earned. In this example, the interest rate and the principal are given. Then, those 2 variables are used to calculate the amount of interest earned, and then that third variable is added to the second variable, principal, to get a fourth variable, the total amount. So let's figure out this next one together. If we add one more statement on, setting principal to 2,000, that will obviously change the value stored in principal. Now, what happens to interest earned and total amount in this case? The answer is nothing. Remember, these variables are just places in memory. When we update the variable principal, it has no effect on those other variables, even though, in reality, principal and total amount would be linked. For the computer, all the assignment line does is change the value in the box belonging to principal. If we wanted to change those other variables, we'd need to actually repeat those lines of code, or write other lines of code in order to assign new values to them. Addition is also defined for strings. When we add 2 strings together, the result is a new string, with one added onto the end of the other. And this process is called concatenation, and it's represented by the addition sign. A variable called first name could be added to a variable called last name to produce a third variable called full name. With my own first name and my own last name as values for the first 2 variables, I could form my full name by combining strings representing my first and last names, which will format nicely if I add a fixed string in the middle consisting of a single space. However, there are no equivalent operations defined for subtraction, multiplication, or division of strings. Hello minus world would be meaningless, as would hello times world or hello divided by world. Likewise, most arithmetic operations between different types aren't defined. We can't add a string with an integer. It's an undefined operation. 1 plus pizza does not give us 1 pizza. Now, an exception that you may come across is that in Python, we can multiply a string by an integer to get the string repeated several times. But don't let this rare exception distract you from the larger point that data of different types normally don't mix. Okay, let's practice. Say you have a variable called number of weeks that has some value, say 26. And say you wanted another variable that holds the equivalent number of days. What line of code would you write to compute the number of days? Well, we can define a new variable, number of days, and use the first variable to assign the new variable a value, that's number of weeks times 7. Okay? What if you had a variable containing a city name, like Los Angeles, and another containing a state name, like California, and another containing a string that gives a postal code? What if you wanted one string that was the way you would write this information in a US-style mailing address, where you have city, comma, state, space, zip code? How would you do this? Well, we could create a new variable named address, and we could assign it a string formed by concatenating the city name with a comma and a space, and the state name, then a space, then the zip code string. Note that the zip code has to be a string before we can add it onto the other strings in the address. Let me explain one more thing that might not be apparent at first. We'll often want to change the value stored in a variable. After all, it's a variable. It can vary. The box is one size fits all. When we have an assignment, the processing of the right-hand side is done first to get a value, and then it's assigned to the left-hand side. But if you think of the assignment as an algebra statement, it might appear to violate basic rules of math. For instance, we can have a command like x equals x plus 1. Let's see how this code works. We first encounter the line x is assigned 3. And so this sets up our variable x, and it puts the value 3 into its box. When we come to the next line of code, we'll first look at the right-hand side, x plus 1. Since the current value of x is 3, the computer evaluates this right-hand side to determine that it should be 4. It's this value of 4 that then gets assigned to the variable on the left-hand side of the assignment, which in this case is x. Notice that the order is important. The computer first evaluates the right-hand side to determine what will be assigned, and then it assigns it to the left-hand side. Remember earlier in the lecture when we had y equals x, and we later changed the assignment to x and found that it didn't change the value of y? Well, the same thing holds here, even though x is on both sides. We could have had any expression on the right-hand side that involved x, and it would have used the original value of x for the computation. Only at the very end would the new value be placed into x on the left. The particular case of increasing the value of a variable by some amount is actually a very common operation in programming. We often find ourselves doing things like counting. And just like a child counts by increasing the number of fingers, adding one more finger to however many were already there, in our programs, we're going to want to add one more to whatever is already there. We might be counting how many times a user enters something in, or going through every item in a large group. For this reason, there's actually a special command, which you see in the example here for y. The plus equals symbol gives us another type of assignment operator that we can call increases by. But in this case, it computes the right-hand side, and instead of just placing that value into the variable on the left, it adds it to the left-hand side. This command, y increases by 1, means the same thing as if we had written y is assigned y plus 1. There's a similar command, decreases by, written with a minus n equals symbol, that lets you subtract the value on the right-hand side from that on the left. You see an example here with z. There are also multiply by and divide by commands as well, and you see examples in m and n. Let's try an example. Let's say that we had a bank account with a starting balance of $1,000. Then, let's say that we had a withdrawal of some amount, say $20. How would we compute the new balance? Well, we would use one of two commands. We could assign balance a value of balance minus withdrawal amount, or we could say balance decreases by the value of withdrawal amount. Either way would perform the same subtraction and give the same answer. Now, the third critical aspect of a computer is the input and output, or I/O. Computers can take input from a variety of sources and send output to several places. Now, as for the rest of the stuff that you see inside of a computer, for the most part, it's handling I/O. There are ports used to connect the keyboard or mouse. There are connections for output to video cards or to files, either on hard drives or on removable media. You can also connect to physical devices like printers or robot motors. This is where data comes in from storage, or over a network, or from sensors attached to the computer. And as you can tell just from looking, a lot of the computer is devoted to input and output. Now, let's assume that our input and output uses a simple text window on the screen. Any input will be from a person typing something into that window via the keyboard, and any output will be text written out to that window. Within Python, the print command is a way of printing a line of data to the screen. The print command consists of the word print followed by parentheses. Essentially, the material inside the parentheses is going to be printed out. We can also print out multiple items, just listing them in the parentheses, but separating them by commas. Now, it doesn't make any difference if you leave a space after each comma or not. The print command will print one space for each comma when it displays the results. One other thing to note. If we want to start a new line, we can print out a string with the code \n inside. The \n is called the new line character, and it's interpreted as end this line and go on to the next one. So let's look at some examples to illustrate. We start by creating three variables: A, containing a string, B, containing a floating point number, and C, containing an integer. The first print command just prints the value of the variable A, which in this case is the string John. In the second print statement, we print out variables A, B, and C. The values of each are printed, separated by a space. So we get John space 3.14159 space 100. Our next print statements print out hello, followed by a new line, followed by world. Indeed, hello and world are printed on different lines. Now, because we separated the terms by commas in the print statement, there's actually an extra space printed before world. If we concatenate those three string terms with a plus sign, we could get rid of this extra space. Finally, notice that we cannot concatenate numbers with a plus sign. Whenever they're defined as numbers, the plus sign means addition, not concatenation. To get input from the user, we have a Python command helpfully named input. This can be used to get information that a user types in. Notice that there are parentheses after the word input. This is going to be common for most commands. The input command is put as the right-hand side of an assignment statement. It gets whatever a user types in, so that it can be assigned to whatever variable is on the left-hand side. To display some text on the screen to prompt the user for input, the input command also lets us include a quoted string in the parentheses. This will be printed out right before the user types in input. In the first line that you see here, the input command is going to print the text, "What is your favorite color?" and then wait for the user to type in a value. That value is going to be assigned to the variable question3. So, suppose a user types in the value blue. This assigns the value of blue to question3. And when we print out question3, we indeed see blue prints out. Now, we don't have to give the user a prompt to get input from the user. If our program has an input command that doesn't include a string in the parameters, the program just waits for the user to type something. In this case, I'm just waiting on user input that I'll assign to the variable b. So, if I type in my name John, then the string John gets assigned to the variable b. And the print statement will verify that the value being stored is the same one that was entered. Input and output, where we won't have any user prompt, is common when we turn to files for input and output. With files, we use commands called open, read, and write, and we don't give files any prompts before reading from them. In any case, input and print alone already give us enough to write many programs. The idea of type becomes especially important with input. In these lines of code, the first two lines assign variables a and b by asking a user to input a value for each one. Let's say that the user inputs 1 and 2. The final line is an output statement. What do you think is output? Well, you might be really surprised to learn that the output is not the number 3, but rather 12. Why did this happen? Well, when we read data with the input command, the data we read always comes in as a string. Let me say that again. Whenever we read data using the input command, even if the data is numerical, the input data always comes in as a string. So what happened? We didn't actually read in the numbers 1 and 2. Instead, we read in the character string 1 and the character string 2. So, because of the way that the input command works, both variable a and variable b were actually strings, not numbers. And so, when we added a and b together, even though they looked like numbers, we were actually getting a string concatenation, not an addition. If we wanted to treat these like numbers, we would have to convert each one from a string to a number. Turns out that that's really easy to do, but we have to remember, data is always input as a string. To convert a string to an integer, or to a float, we write int or float and then we put the string in parentheses right afterward. Here we have two strings, a and b. We can create an integer, c, from the value of a's string. And we can create a floating point number, d, from the value in b's string. So what would happen if we tried to do something weird, either trying to call an integer like 1 a float, or trying to call a decimal an int? Well, the first line, where we convert the string 1 to a float, still works fine. 1 becomes the number 1.0, which is exactly what we'd hoped for. Obviously, the integer 1 is the same as the floating point number 1.0. However, there's a problem trying to convert a string, such as 3.14159, directly to an integer. Python has no direct way to make a string with decimal places into an integer. We first need to convert the string 3.14159 to a floating point number, and then we can convert the float to an integer. To go from float to integer, we can either truncate or we can use rounding. To truncate, we can, just like with a string, write int parentheses and then the float to convert inside the parentheses. This will truncate the floating point number to an integer. That is, it'll drop off any of the fractional part. Alternatively, we can write round parentheses and then the float to convert inside of those parentheses. In this case, we'll round up or down to get the integer closest to that floating point number. Let's go back and fix the example where we concatenated 1 plus 2 instead of adding them. If we convert the input to an int before assigning it to a and b, then a and b are integers, not strings. Notice that we enclosed the entire input statement, including its parentheses, in parentheses. Just like in math, you handled the stuff inside the parentheses first. So, for each of our two variables, we read the input from the user first, and we get the result. Then, because the input command always brings in data as a string, we convert that result to an int, and then it's that integer that gets assigned to a variable. So, when we use the print statement to add the two converted variables together, now we do indeed get the sum 3 rather than the concatenation 12. You need to be careful to convert to the correct type when you read input. Let's try a couple more examples. Say we wanted to get the user's name. What code would ask the user for their name and get the answer? Well, we'd use the input command, passing in text such as, "What is your name?" We'd assign this to a variable, like name. Now, say we wanted to greet the user personally, starting with hi. How would we do that? For output, we'd use the print statement. We could either print out two strings, one being hi and the other being the name, or we could print out a single string, formed by concatenating hi with the name. Notice that in the first case, there's a space inserted before printing the name, while in the second case, we have to explicitly include that space in the text. Practice input and output commands for yourself until you're very comfortable with them. For programmers, a variable is a box in short-term memory, a place with a label where we can put a value. When we assign a value to a variable, it does not mean that the variable and value are equal, only that we've temporarily put a value into that labeled box. Basic operations in a computer can have different outcomes depending on the type of variable. An expression written with the plus symbol will add two numbers, but it'll concatenate two strings. Python's input command always brings in data as a string, even if it's numerical data. So, we often need to convert data to a different type. When we combine variables with either operations or input-output commands, we get statements that let the computer do virtually everything we regard as impressive. To preview some syntax for our next lecture, if you've understood this lecture and you're ready to continue, then in the next lecture, we'll learn a new way to make a more powerful statement, known as the conditional. Else, review this lecture again. Okay, let's do a math example. Say we wanted to compute the area of a circle in a program. First, we'd want to read in the radius of the circle. What would that part of the code look like? We start with an input statement, and we pass in some text telling the user to enter a radius. Notice that since we want the radius to be a number, we'll have to convert the input from a string to a float. Okay, now say that we want to compute area. What would that involve? Well, there's a few ways we could do this, but one would be to create a variable, pi, that we set to the value of pi to a few digits. Then we can compute area by taking pi times the radius times the radius. We could have just put the value of pi in that equation instead of defining it separately. Now finally, say we wanted to print out the result. What would we do then? Well, we'd again have the print statement. We could print out the text and the answer separated by a comma. Or a different option would be to concatenate the area with the text. Notice that to concatenate, we need two strings. Since area is a float, we have to first convert the float to a string. Fortunately, it's easy to do that. We just use an str command, similar to the way that we used int or float to convert to an integer or floating point number. That's it. We could expand this program to tell us all kinds of other information if we wanted to, like the circumference of a circle or the area of a different shape. Keep playing around with it, and I'll see you in the next lecture.